And another quantity that we need now to look into is the shear strength. The shear strength is another quantity that needs some discussion because due again to the anisotropic behavior, the shear strength is highly dependent on the shear plane where we are going to measure this quantity. So, as you can understand, if the shear plane is a plane intersecting the fibers, then we will have a very high resistance. Because of course we will need to break all the fibers in order to make the two pieces of wood shearing off. So this is called vertical shear. Another possibility is that if you have a shear plane which is parallel to the fiber. Actually we can have two different kind of shear strength depending on the shear plane parallel to the fiber. Because you can see here we have a plane parallel to the fiber, and we have a shear direction which is basically in the longitudinal direction. If you remember, probably from last Monday, you learned that in our trunk, if this is our trunk, we have two different directions. Okay, let's do the whole direction. If this is our trunk, you remember that there is one direction which is called longitudinal. So this is the direction parallel to the fiber. And then in the plane of the trunk, this is the growth ring, here we can have two different directions. The direction, the so-called radial direction, so the direction perpendicular to the growth ring, and the tangential direction. Tangential direction is the direction in the same plane, the cross section, but perpendicular to the radial direction. So basically, it's the direction tangent to the growth ring. So, when we cut a beam from here, for example, because we are cutting this beam here, this is a plane, basically, if the shear plane crosses, is perpendicular to the fibers, like in this case here, then, of course, in order to have a shearing of these two pieces of wood, we would have to break the fiber. Okay? So this is a beam. Now we are looking at the beam as if it was vertical, but usually this beam, of course, is this way. So we load our beam. And we have some shear. This is the cross section that we usually check for shear, right? This is the cross section. Then we calculate the stress distribution, rectangular cross section, we use Juravsky, for example. We have a parabolic distribution. Now max equal the shear B divided by the shear area. Shear area is 2/3 of the area. So we can expect basically to have a shear problem here on this fiber here. Now, how would you expect that if there is a failure for shear, the beam would fail here? Suppose that the shear is exceeding the shear demand is exceeding the shear capacity. How would you expect that this beam made of wood is going to fail? Yes, what? What is going to break it? Eh? I mean, if we think about, for example, think about reinforced concrete. The reinforced concrete machine was very complex, if you remember well. You remember the crack configuration. Reinforced concrete, you have the load, then first, before you have the activation of the reinforcement, you have some cracks forming. Which kind of direction did these cracks have? Remember? Incline 45 degrees. 45 degrees. So, if this was reinforced concrete, how would you expect the failure to occur? Suppose, okay, this is the reinforced concrete. How would you expect the failure to occur? This way or this way? Which one? Huh? Okay, that's okay. Suppose that we know that the shear starts from here. How does how does it go? This way, this way, this way. This way. So in the shear area, if you remember well, there is this failure mechanism, the Ritter-Mersch truss. Basically, the crack is going to fall more or less 45 degrees. Because you can find out, if you remember, if you have a homogeneous material, homogeneous isotropic material, you can find out there are some isostatic, compression, isostatic, and tension, and so on. If you remember well, around the neutral axis, more or less, you have an inclination of the main direction of 45 degrees. Now, in theory, how would you expect the shear crack to form? Yeah, but we said the 45 degrees usually have the isostatic compression. So, can we have a 45 degrees also with timber?
No.
No, why?
Because of the 45 degrees means the 45 degrees means
to do what?
And
If you want to have a crack formation,
the fiber are too incurved.
yes.
So
45 degrees means that we would have to fail the fiber. So this shear plane would have to intersect the fiber and to basically to break them. It's easy to break the fibers. No, because as we said before, the fibers are very strong. What is easier to break is what?
the
The matrix. What is the orientation of the matrix in this case? Well, of course, it's not the orientation of the fiber, but if this is our fiber, so when I go on the cross section, this is the tau, remember? So this tau I apply in this way. So this means that this tau would have to break the fiber. So we would have to have a crack like this. Is it possible to have a crack like this? Even worse. Some of you are saying, okay, well, we can break the fiber, so we can have a crack formation like this. How is it possible, since the tau are oriented in this direction, to have a break like this? This is the weaker plane. So we can expect to have a shearing on a plane parallel to the fiber. Because this is actually the weakest plane. In this way we're going to break the middle lamella. So the weak matrix. Is it possible for shear to have a failure like this, since the tau are oriented over the cross section this way? perhaps to get back to what we learned in mechanics of structures with Professor Longo.
Yes, we have the same on the.
If you remember, there is one theorem or one conclusion which is called reciprocity of shear stresses. What does it mean, reciprocity of shear stresses? It means that if we're going to, for example, to isolate one small cube here, this material, this is our cube, this is tau. If you study the equilibrium of this cube, we will find that exactly the other direction, the direction, in this case, parallel to the fiber, we are exactly the same tau as in the vertical direction. So this means that we have also some tau here. And those tau acts on the weakest plane, because the plane intersecting the middle lamella. So this means that in timber, if we get a shear failure, the shear plane, the shear cracks will always fall where we have a maximum shear, which means close to the support, and the shear crack will be more or less horizontal, will be parallel to the fibers. Okay? This is called longitudinal shear. So longitudinal shear is a shearing of two pieces of wood on a shear plane parallel to the fiber direction, and the direction of shearing is parallel to the fiber themselves. In other words, the shear plane is parallel to the fiber, and also the shearing direction is parallel to the fiber. Okay? This is a typical shear failure for timber beams. However, in other structures, we will see in two-dimensional structures, for example in cross-slab panels, we will see that there is another possibility of shearing. So, again, if we look at this beam here, the shear plane could be the same, but the shearing direction could be perpendicular to the direction of the fiber. So the plane is the same, but if you look at now, this is the front of the beam. If this is the front of the beam, shear plane, horizontal like before, parallel to the fiber, but the shearing this time is across the width of the beam. In this case, the shear resistance of the timber is even low. Basically, this would be a shearing of the beam in the tangential direction. So this is called rolling shear resistance, or in Italian, literally, taglio da rotolamento. So when we design a beam, the normal failure mode is longitudinal shear, which means shearing parallel to the fiber in the direction of the fiber. When we design two-dimensional structures like panels made of plywood, so 2D, then we will have to consider also the rolling shear, which is the shear in the opposite, in the direction, in the tangential direction. So the shear in the other direction, always with a shear plane in the middle of it. Okay? Now a question. Sometimes, when you look, particularly when you look, okay, perhaps we can just show this, which is what we've just been discussing right now. Vertical tilting shear, longitudinal sliding shear, and rolling shear. Vertical tilting shear is very high, and longitudinal shear is higher than rolling shear. So rolling shear is the weakest one. This means that due to this equivalence of the tau in the two different directions, this means that in their reality we will never be able to achieve a failure like this. Because since the shear demand is always the same in two directions, for sure, first we will get a failure for longitudinal shear. We will see in fact that in the regulations, we never find a value for vertical tilting shear, we just find longitudinal and rolling shear strength. Okay? Now a question. When you look at, particularly when you look at old timber beams, very often you will see that there are some cracks. Okay? Ah, the tessure. These cracks very often are inclined. They are not horizontal, they are inclined. Why is that? Your opinion? Sometimes we also quite a lot inclination.
The structural has to straight.
No, you're being it this way, and then you find some cracks this way. Why is that? Which defect? Great deviation. Okay? Usually this is not shear failure. This is crack due to shrinkage, due to the influence of the moisture content. We will discuss this later. And they are usually inclined because of the defect, because of the grain directions. It's not because, like in reinforced concrete, the shear cracks are inclined 45 degrees. Okay? Those are due to the defects, to the spiral line fiber. Remember that usually you need to check if you have a real shear failure collapse, you need to check this in the area where the shear is maximum, so basically over the support, if you have a simply supported beam. If you have a shear failure, you may have a horizontal or slightly inclined crack, and then, of course, since this is going to reduce your strength, so consider, suppose that this is your beam, you have a shear crack like this, it's clear that when you go to do the shear strength verification, you need to consider that your formula tau equal to 3/2 of V divided by B times D. This B must be reduced because here you have a crack on the neutral axis. So in this case, you need to be careful. You need to go, if you want to reuse the timber B, you need to go and measure the depth of this crack in the formula to apply a reduction coefficient. Okay? So, how to avoid shear failure? We will see later on also in the course that there are some ways to reinforce a timber beam using not normal reinforcement like in reinforced concrete design, but using some screws. So basically in timber, I would say very often we use self-tapping screws, which means viti autoperforati, that we can basically screw inside the timber, and these screws may provide some reinforcement against shear. So basically these screws are able to take some, you see that the screws are oriented along the tensile direction, so we orient the screw such that they can work in tension, and they can provide some shear resistance along this possible shear failure plane. Remember also that if you have like a notch like in this case, this point here is a very delicate point, I would say, because when you have a corner like this, you have a stress concentration, and very often you have here a crack formation. So the best thing would be never to cut a notch, but if you cut a notch, you can expect a crack. And then very often when you cut a notch, it would be better to reinforce the beam with some screws in order to prevent the propagation of the crack. You may also have a small crack, and then if you put the screws, this crack does not propagate anymore. And then you can have the full shear resistance of the beam. Okay. Any question about shear? Yes. What is it? No. must basically tie up the part of the timber above the crack with the part of the timber below the crack. So the crack should be more or less equal. So the screws has a strength as a withdrawal strength, so a strength against the resistenza all'estrazione. So in this case, this screw, thanks to the threads, grazie alla filettatura, by working in tension, prevents the sliding of those two parts of wood with respect to the crack, to the shape crack.
Un'altra cosa, dico, alla punta della vite, che è considerato un difetto, perché lungo tutta la vite
no,
insieme alle due parti, ma sulla punta dove diciamo.
Why should be a defect the point of the screw?
Perché comunque va, diciamo, non è più una zona che come proteggere, una parte di sopra e una parte di sotto.
No, but this is a setup in screws. So this one, autoperforante, because inside it doesn't damage too much everything. So it's not it works in this way. Other questions about the shear strength? Okay, if there are no other questions, then we come to another important topic, which is about basically the need to grade the timber, cioè il bisogno di classificare il legno. So, until some years ago, you could go to a tree, to cut one tree. Of course, it's not so simple to cut a tree. Sometimes trees have some kind of for the legislation, you can't just cut down a tree. You need to have a special permit and so on. But until some years ago, if you had a permit, you could cut down a tree, you could cut your own beam, and then you use your own beam in structural design. Nowadays, all the timber that we can use in structural design should be classified. The actual name is grading. So when we talk about timber, we talk about basically grading of timber, which means assign the timber to a certain strength class. And meaning also that your timber must arrive in the building site with a stamp showing the strength class and some well-defined properties, basically. And now we want to understand why. Why do we need to classify? Why do we need to spend time and money to basically grade the timber? Because we will see that timber grading needs some time, needs someone going there to look for defects, measure the defects, or needs to do some non-destructive tests like applying a load and then find out the module of elasticity. So why do we need for each piece of timber to lose time and money to do this grading? This is what we want to understand. And we will understand this by answering to the very simple question. How much does the strength and stiffness vary of the timber within a species and a grade? What does it mean a species? Wood species, for example, I use spruce, abete, or I use faggio, beech. So if I cut 1,000 plants of spruce, how much is going to change the strength of these plants? Same plants, if you want, same size. I want to test in tension, in bending. 1,000 value, how much are those 1,000 values expected to change? Little or a lot? Well, if you think the wood is a natural material, you can expect that there will be some variation, of course, in the properties both of strength and stiffness. In fact, we can see that the answer is much more significantly than for steel and concrete. Why is that? Again, the fault of this is the effect of the defects. If we had a wood without defects, then it would be very constant. But since we have the defects, not more or less big, the result is that this 1,000 pieces of wood will have quite different value of strength and stiffness, because all of them are affected by the defects. You see, the strongest pieces may be far or more times the strength of the weakest pieces. And this is the need, and then the need to grade the timber. So, to assign a timber to a certain strength class, because otherwise we will have a too large scatter of results, which will result into a very low characteristic strength of wood being used in the design. So this is an example. This is not about our wood, it's about New Zealand wood, just because we can work there for a period, but in Italy would be, in Europe would be very similar. So as I said before, we have a wood species. This case was a wood called radiata pine, that is originally from Chile, that they are using in New Zealand because it grows very fast. So you take 10,000 specimens, so 10,000 boards out of this radiata pine from different locations from all New Zealand, and then you do a test. What kind of test? We learned before, we have to do a 4-point bending test, for example. So all of those pieces are tested under 4-point bending. We increase the load, and we want to calculate the FM, bending strength, that we saw before. That in this case, as I said before, in New Zealand, it's called modulus of rupture, which is exactly the same as our bending strength. So for each piece of wood, we calculate the bending strength, and then we calculate the module of elasticity. How do we calculate the module of elasticity? Well, when we apply a load here, we measure the deflection. We measure the deflection. We have for example, linear voltage displacement transducer, some instrumentation to measure the displacement. And we know that if the load is not high, we have an elastic relationship between the load and the deflection. There, again, the failure. So, for a load which is not too high, for example, 0.4, the failure load, PF, let's call it 40% of the failure load, you measure the deflection, eta F. Sorry, eta, let's call it only eta. Then you know that from the elasticity theory, you can find a relationship like eta equal to a constant times P times L cubed divided by EJ. So P would be the load, 0.4 PF, for example. L is given, E is the module of elasticity, and J is the second moment of area of the cross section. So from this, you can invert the formula to find E. Module of elasticity, E, will be basically K P L cubed divided by eta times J. So you know this quantity, P, you measure the load that you have applied, you measure the deflection, you can find out the module of elasticity. So for each piece of wood, you said we took 10,000 pieces of wood, we tested them, from each test we get 10,000 value of module of elasticity and 10,000 value of module of rupture, so bending strength. So each of those points represent one specimen. Okay, so we do this. They've done some years ago this exercise in New Zealand, and that was the result. Now, how can we comment about this result? Is this result regarding, in your opinion, a reliable material? Would you define radiata pine as a reliable material with this cloud here of points? Well, if you have a look, some values, you see there is one specimen having a module of elasticity of 3 gigapascal. Just for your recollection, we are talking about gigapascal here, so concrete would have 30 gigapascal. timber. In this case, this specimen will have 3 gigapascal of module of elasticity and 10, let's say 8 megapascal of bending strength. This is one specimen. Then on the other end, there is one specimen here you see having 18 gigapascal of module of elasticity, from more or less 7 8 times the other, and the strength up to 80, even more. So 10 times the strength of the specimen before. So as you can see, the scatter is quite significant. Now, if we wanted, for example, in this case, to avoid any grading, to avoid any classification. So they say, okay, I want to cut a piece of wood and to be able to use immediately without any classification, without any grading. Which value of module of elasticity should I use, and which value of characteristic strength should I use in design? Well, in terms of strength, you know very well from the limit state design, you need to use the characteristic value of strength. So which value would be the characteristic strength in this kind of scenario here? We need to go, if we said, if we have 10,000 specimens, the 5th percentile, the characteristic strength, if you remember well from 1 or 2 years ago, is the 5th percentile. 5th percentile means that I need to find the value of strength such that no more than 5% of my specimens have a strength lower than this. So I need to move, you see this horizontal line, up and down, until I get how many points here? If I have 10,000 points, I need to move this line until I get 5% of 10,000, which means 500, right? 500 points, 10,000, 1% of 10,000 is 100, 100, yes, 500 points underneath the line. So in the end, you see I would get a characteristic strength of what could be this? 18, 16, 16. So I could use only one class, only one strength class, this one, without any grading, without doing anything, just cut the wood and use immediately, but I should use with 16 megapascal of characteristic bending strength. Meaning that, you see, the large majority of wood would actually be penalized, because I'm using value of strength which is much lower compared to the strength that I have in most of the spaces. But if I want to be sure that I don't have any problems, I should do it this way. Which value of module of elasticity should I be using? Also here we need to remember what do we need a module of elasticity for. You told me before, module of elasticity is needed for, can you repeat me please?
Limit of serviceability.
Limit state of serviceability. Of serviceability limit state. Now for serviceability limit state, if you remember, we said that in this case our, let's call it design value, is which value?
The minimum value.
It's the mean value. It's the mean value. So this meaning that in this case I should move this vertical line right and left until I get how many spaces on one side and how many on the other? How many points on the right, how many points on the left to get to the mean value? 50%, which means 10,000, 50%, 5,000 on the right, 5,000 on the left. And then I will get, you see, more or less 8 gigapascal. Also, in this case, of course, we have some of the wood is penalized, but this is a mean value. It's not a big problem. The big problem is the strength. So the strength will be very low. So for this reason, the idea is that when we talk about wood, since the scatter is much higher compared to steel or compared to reinforced concrete, what we have to do, we need to grade the wood. What does it mean to grade the wood? It means to introduce some rules for example, a visual grading, and going to measure, for example, the diameter of the knots, the number of the knots, diameter of the knots, the position of the knots, and so on. That's allow one person to assign this piece of wood to a certain strength class. Or, the other possibility, we see it's a machine grade. constructive test like this to apply a value of log to measure the module of elasticity, and from the module of elasticity to get a value of strength which is more or less reasonable depending on the module of elasticity. This is called basically grading of. In Italia come say, devo classificare il legno, assegnarlo a una classe di resistenza. For example, in this case, if rather than having only one strength class, we would decide to have 3 different strength classes, what would we have? You see, we could have a strength class of the specimen which are the worst one, so basically to have a lower strength class. For the lower strength class, we will get, you see, a lower characteristic strength. Before we had 18 or 16, now we would have 12. But only some specimen would belong to this strength, to this lower strength class. Then we would have a medium strength class. In this case, you can see that the characteristic strength would be much higher, 26. And then we could have a higher strength class. In this case, we would have a characteristic strength of 50. So in this way, as you can see, we start optimizing the pieces of wood. So the worst one, of course, they go to a lower strength. But then the best one, they go to a better strength class. Meaning that we can use the best pieces when we need more, and the worst pieces when we need less. Now, I have a question for you. You have 3 pieces of wood. In one piece of wood, you have few knots, big. In the other, you have many knots, much smaller. Which one would you prefer if you have to build a house for you? Why? Remember that the knots are like holes. So it's better to have a big hole covering all by cross section, or maybe small holes spread out more or less everywhere. Of course, not only a hole. You can't have infinite small holes. What is best? Or less worse? What is less worse? To have only one big hole, as big as this, or to have smaller but more spread out?
Many and smaller.
Many and smaller. Not too many. Let's say not too many, but smaller. Why smaller? Think about here. There's a limit case. Only one as big as the cross section. What is the strength? 0. If I have several of them, and they have more or less evenly distributed, of course not too many, because if I have infinite, of course, so here 0. There are some of them, but evenly distributed, I can have a less reduction due to the knots. It's clear to all of you? This is another concept which is quite important. So I would like that you tell me if this is not clear. Of course, when I say many, I mean more, but not too many, not infinite. Of course, if I have a situation like this, very small, but all, clear, I cannot get anything of this. But if I have one here, one here, one here, one here, one here, one here, this is better than having only one here. It's clear one, okay. If you want, on the same area of knots, it's better to have only one or more spread out. On the same total area, it's better to have more spread out. So if I have only one, you see here, then here the cross section is almost at the end. Okay? So the idea is that you see this table, this blank here, A, few big knots, is the one with the worst properties. Those are the probability density function that we studied 2 years ago, 1 year ago, about the property of wood. What we will call Gaussian or normal distribution. In this case, you can see the curve is no longer symmetric, it's not a normal distribution. This is usually, we consider a log normal distribution. So the logarithm of the strength is normally distributed. This is a kind of distribution if you use 14 or maybe 13. But this is not important anyway. Important is to see that, you see, as soon as you move from few big notches to more lower diameter notches, you see that the curve moves towards right, which means that the characteristic strength is basically increasing. Clear? Good. So now, another important thing that is the basic of a kind of method to grade the wood, grade the timber, is that, as you can see, there is some correlation between the modulus of elasticity and the modulus of rupture. There is a general trend. So as soon as the modulus of elasticity increases, also the modulus of rupture increases. Of course, there is a scatter, because, for example, take the value of 8. If I measure a value of 8 gigapascal in my test, you see, I can go from a value of modulus of rupture from, let's say, 12 till 50. So still a large variability. But anyway, you can recognize that there is a trend. The trend is that the higher the modulus of elasticity, the higher the strength, the bending strength. Why is important this correlation? Correlation is important because when I use timber, I want to know the strength. The only way to calculate the actual strength is to break the timber. But once I've broken my piece of timber, I cannot use it anymore. So I need to find a kind of non-destructive technique to measure my bending strength of wood. Now, measuring the modulus of elasticity, sorry, I forgot to switch it off. So measuring the modulus of elasticity of timber, measuring the modulus of elasticity of timber is a non-destructive technique because I can apply a small amount of load, not the failure load, of course, 40%, even less than the failure load. I can measure the deflection, and then by inverting this relation, I can find out the modulus of elasticity. Because the first part of this diagram is very linear, it's elastic, linear, elastic. So by applying a small amount of load, measure the deflection, we get the information of the modulus of elasticity. So once I get the modulus of elasticity, then I can find a certain range value for what concerns the modulus of rupture.
A question.
Yes.
How much in Italiano forse?
No, faccio in inglese. No, tutto non solo per me, anche per voi.
The failure tension change between 3 and 3.
The failure tension change between
3 and 3.
what do you mean? Yes, so between the trees, you mean? Yes. Yes, in general, it changes also depending on the tree.
And if we take a piece of this,
Yes.
how we can correlate this?
The idea is that, for example, I can tell you what we are doing right now, that we are trying to use the Italian beech. Beech, it's an English word to say in Italian would be faggio. It's a tree that we have quite a lot here. Since we don't have grading rule, what we are doing now, we selected several planks of beech in different locations, for example in Friuli, in Abruzzo, in Tuscany, in Sicily, and so on, from different trees, a certain number, 1,000. Then we broke all these pins, these planks, and not us, some other researcher from CNR Ivansa, they try to find a correlation between the modulus of elasticity and the modulus of rupture. To find a good correlation, this correlation here is not enough. So what they do, they couple the measure of the modulus of elasticity with some scan of the surface. In fact, the other way to do the strength grading is, rather than to measure the modulus of elasticity, for example, you see here, we have a timber beam going through this machine. The machine, you see some rollers because the beam it moves through the machine. When it moves, the load is applied here, the deflection is measured, and so immediately we can get the modulus of elasticity. So each piece of wood will have a modulus of elasticity. In general, as I said before, the correlation is not enough. So what they are doing usually, they couple this measurement with a scan of the surface. Why is it important to scan of the surface? Because, you see, there are some rules also for visual grading. What does it mean, visual grading? It means that by measuring the location and the diameter of the knots, we can get some good correlation with the strength of the wood. Because again, what counts in the strength of the sawn timber is not the strength of the clear wood, so the wood between the knots. What counts more is the location and the dimension of the knots. So in this case, what I was saying before, we are testing, we have tested like, I don't know, 1,000 planks out of made of beech. Then they have tested to failure. Before they had scanned all these planks to find out the location of the knot. And then what they do, they try to correlate the position of the knots and some parameters with the module of rupture that they find out, in order to find some rules for this visual grading. In fact, now we have some rules. You see, this is taken from an Italian regulation. Now we don't want to go into detail about this, just to show how it works. Who does usually this visual grading? It's not an engineer, even though you could do it, but it's a wood scientist. So usually who does the visual grading? It's a person who has got his degree in forestry with specialization in wood technology. So they are trained to do this kind of grading of wood. So this is taken, as I said before, from the regulation. You need to measure the moisture content. Then you see, you need to measure the knots basically. So to go on the, no, unfortunately I don't have here a piece of wood, some timber, but unfortunately this piece doesn't have any knots here. So we need to measure the knots, the position of the knots, where these knots are located with respect to all the faces of the wood. For example, here you see this is a piece of wood. There is a knot here in the middle of the face. You need to measure the diameter and the position. You see there is another knot here. This knot, it covers all the sides. So we need to scan basically the knots on all faces of our specimen. We need to measure the grain deviation. Remember before we were talking about the different knots, mostly diameter, location of the knots, but also grain deviation. So if this is the fiber, you need to more or less to find out the inclination of the fiber with respect to the axis. You can use this kind of instrument here. It's called graphietto, I don't know the name in English, but it's just a matter to find out how many degrees is the inclination of the fiber. Then another quantity that we need to measure here is the thickness of the growth ring. You know what are the growth rings? For example, this one, there are different growth rings. So we need to take basically a line like this, of at least 75 millimeters long. You need to measure how many growth rings you have in between. So then you do 75 divided by the number of growth rings. You get the mean value of the growth ring, of the thickness of the growth ring. Why is it important the mean value of the thickness of the growth ring? Because the smaller the growth ring, the higher the density. So, for example, I was telling you before about this radiata pine, which is a plantation used in New Zealand. Basically, they plant the tree, and then after 20 to 25 years, the tree is ready, very big. But of course, it grows very fast, but the growth ring is very big. It's like 1 or 2 centimeters. Meaning that the density is very low. If the density is low, I don't know if Dr. Schmidt already told you about the density, but the density low means that also the properties of the wood are a bit low. In fact, the most important distinction between for the wood is between softwood, which is conifer, and hardwood, which is deciduous tree. if you lift a plank of hardwood, you will recognize immediately it's a hardwood because it's much heavier than the same plank out of softwood. So density of hardwood would be between 500, 600, 700 kilograms per cubic meter, while instead for softwood is 300, 400. So it's completely different. So the higher the density, the better the mechanical properties usually. So for this reason, it's important also to measure here the thickness of the growth ring. So for example, here you take a line and you measure and then divide for the number of growth rings. This is another parameter that is used for what is called visual grading. See here this exercise done for number of section. Not very complex, of course, but the complexity is that when they do the visual grading, they don't have time, to spend. They have to classify a piece of wood in less than 1 minute. So you have to have very good eye, very good training to be able to understand immediately if the defect is good, is bad, and so on. And then another thing that we need to check is about these cracks. Those cracks we will learn later. Often they are due to basically shrinkage of wood. So when the wood, when you dry the wood, you will see that there's a strong effect of moisture content. So usually the wood must be dry. When the wood is dry, then you get some cracks. It will be split if the crack extends to all the thickness, otherwise it's called check or shake. This is in Italian cipollatura. You see, this is taken from this regulation. The regulation says that if you have this defect here called shake, if you have the shake in this way here, this is not allowed. So if you have a beam, at the end of the beam you find this defect, you have just to reject the beam, you cannot use it. This one, E, not allowed because it's concentric. D, this is allowed because it's more in the center, and so on. So there are some rules, like the one that we can see now, that we can follow when we do the visual grading, based on all these quantities that we saw before. Another quantity we need to measure is if there is, you see, a cross section. What's happening is sometimes when you cut the wood, of course, since you need to cut rectangular pieces out of a log which is circular, of course, you try to cut as many blocks as you can. So, for example, here in between may be fine. But here, for example, you may have a board which is cut this way, or a board which is cut this way, because here you have the bar. Now, is it allowed to have a defect like this? Is allowed, but with some limitations. See here, you need to measure the length of this inclined side, and then you need to calculate the ratio between this length and the larger dimension of the cross section. You get a certain ratio. Then you can have some other defect like this. You see, these are distortions. When you get your plank or your timber beam, this beam could be distorted. Why there are those deformations? Those deformations usually are due to, again, the drying process. Because the wood, we will also study this later, when you cut a tree, the wood has lots of humidity inside, and then this humidity is going over time to disappear. When the humidity disappears, you have also some distortion, something like this, and of course, those are not allowed if they are too big. If, for example, you see this deflection is too big, then you can't really use the table because you have lots of problems. This one, these distortions are basically due to the fact that when we cut the wood, initially the wood has got lots of humidity inside, and then the wood is going to shrink because the humidity is going to be lost over time. So you will go, we will see it better this later on, you will go from, for example, to 100% of humidity, which means that the wood is more water than the material, basically, up to a situation where the moisture content will drop to 12%. Normally, the normal range of moisture content is between, I would say, 10% and 20%. 20-25% depends on the environmental condition. If you are in a swimming pool, you can go up to 25-22%. If you are, well, in Italy not so much, but if you are in an area like in Colorado, for example, which are very dry, like a desert, then you can go down to 6%. That's the extreme cases. So, when you have a reduction of moisture content, this reduction, since again wood is a non-isotropic material, the shrinkage is different in different direction. This is going to cause this kind of distortion. In fact, the idea is that after you dry the wood should always be plain. So it should be, how do you translate in Italian? Pianato. Okay? Pianato in order to reduce this difference. So this is the way you see to measure, for example, a spring, which is called in Italian tagliatura. What's up there? This one was horizontal. Initially, this was a rectangular cross section. Then we let it dry. This is the result. I want to show you later, but since you asked me, I'll show you later. No, you have a look. Yeah. And this is due to the fact that the shrinkage is different. Let's say perpendicular. Okay, it's a huge difference between, again, parallel to the brain and perpendicular to the brain. Parallel to the brain, moisture content variation doesn't cause any significant shrinkage. Perpendicular to the brain is much more important, and is different radially and tangentially. So tangentially, the shrinkage is twice as much as radially. So for this reason, if you have a reduction of moisture content, an initially rectangular cross section doesn't stay rectangular anymore. You will get some distortion like this. So when we classify a piece of wood, we need also to measure those, you see, quantities. Spring, twist, and so on. So this is a regulation, Italian regulation to do the visual grading. This is important just as an example. Of course, it's not our duty to classify a piece of wood, even though I have to tell you that when you will be an engineer, and you will hopefully work with timber, you might have to answer some questions from the client. The client will tell you, or let's say, you could see that some wood is not very nice. You could see that some wood is full of knots. For example, you might have in your design report a high class of wood, and then you can see that your local enterprise brings you wood that doesn't look so nice. So what can you do at that? Even though it has all the standards and classification, what can you do? First thing to do is, with this regulation, to go there and check a couple of pieces of wood if they comply or not with this regulation. Perhaps you may feel not very confident, but you can try. If you see that it looks like the wood does not comply with the regulation, then you phone to a wood technologist from Florence, from Ivanza, CNR, now it's called IDE, Istituto per la Bioeconomia, and you tell them to come there and check. If they check that this wood does not comply with this class, then you start having a discussion with them and say, look, this is not the wood that I own. So it's very important also for you to have an idea how to do it. Because there is no point that you call immediately one person if you don't. I mean, it's better to try your own to see if there is some suspects. If there are some solid suspects because this regulation doesn't, it seems that the wood does not comply with the regulation, then you call another person, you spend a little bit of money, but at least you are sure. I talk about direttore di lavoro, I'm talking about, let's say, the checking engineer. So the engineer who has to check that the construction complies with the design. It's called checking engineer, direttore di lavoro. So, you see here, modalità di esecuzione, so this is visual grading. The visual grading shall be carried out with the following methods. So, all the faces and all the surface, if this is your piece of wood, you need to control all the 6 surfaces of the wood. Okay? Then you have to apply all the classification criteria that you will see in the following of the section. And then, if it comes out that this can be classified as in 2 or 3 classes, of course you need to take the worst one. And then, if this does not comply even with the minimum strength requirement, then you have to reject. Reject means you cannot use it. You have to use as a final, basically. Okay? So, let's have a look. So this is the first table here. So first of all, you need to understand which wood are you using, so which timber are you using, and where does it come from. Suppose that you are using, you bought spruce from Abruzzo. Well, we don't have lots of spruce here, but anyway, suppose assume that you have some spruce from Abruzzo. You're going to this table, you see, spruce, abete, spruce, nord, because we are centro-sud, abete, centro-sud. So spruce, Abruzzo is here. So spruce, Abruzzo, you see, regular classification, so classification rule, conifere, which will be conifers, 1. Category, there are 3 categories, S1, S2, S3. So our wood, depending on the visual classification, can be assigned to strength class S1, S2, or S3. And we need to use this rule called conifere 1. Now, if you go to see what is this regulation, you will find the classification rule for conifere 1. Conifere 1, you see, this is classification criteria, S1, S2, S3. So, S1, first, smoothie was this aspect here, this one. So, smoothie was the ratio K over H. So, first of all, I measure K, I do the ratio to H, I got a certain value. Suppose I got 1 out of 5. Is this ratio less than 1 out of 8? If I got out of 5, no, it's that. So, it cannot be S1. It has to go to S2. Is 1 out of 5 1 out of 5 lower than 1 out of 2? Yes. So my wood, since I have this problem, can only be classified as S2 or S3. Then we continue. Knots. The area of the knots less than 1/5. We know that since this motion was not compliant, here we need to see if the area of the knot is less than 3 out of 5. So if it covers less than basically 3/5 of the whole width, if this is okay, then it can be S2 or S3. To be S1 should be less than 1/5 of the width. Okay? And then you continue this way. This is a group of knots. This is the width of the growth rings. No limitation. Then here we have the grade deviation. To be S1 must be less than 1 over 14. So 1 centimeter over 14 centimeter maximum. If it is more than this, it goes to S2. But anyway, also for S2, S3, it should be less than 1 out of 8. So you need to do all this exercise, and then you see here the cracks from shrinking, these are allowed, the others are not allowed, and so on. Okay? So in the end, what you have to do for each phase, you need to measure all these quantities, and if you have all of them comply with the column on the left, then your wood can be classified as 1. If only one of those, let's say that they are all complying with this column, but only one is here, then you need to use this column here, S2, S3. So if only one is on the right, then you need to use the right column. It means that your wood will be S2, S3. If there is even only one that does not comply with even this, the wood must be rejected. Cannot use for structural purposes. Clear? So this is the way that we do the visual classifications. not we, usually it's a food scientist. But again, when in doubt, when you be a check engineer, you get, let's say you order some solid wood that in your opinion should be a higher strength class. You find lots of knots, you may think that maybe something's wrong. So you go to measure, you use this classification here, and if you find actually that the wood is S2, S3, or even rejected, more than one piece, then the best way to do, if you want to be sure 100%, again, you call a wood scientist, wood technologist, who will confirm what you have done so far. And then you start discussing with enterprise. It's clear? Okay, now, but what does S1, S2, S3 mean? So far, we just know if this piece of wood is S1, S2, S3. What is the actual strength class? You see, there is this regulation in this table saying that, for example, we said before, spruce from center of Italy. So will be Abete Italia. You see? Abete Italia. So S1 doesn't have any class. S2 class C24. S3 class C18. And here you can see the properties. The properties in the usual design. So if you have S1, if you are classified this S1, since S1 does have a number, you need to take the closest number, which is S2. So you get 25 of basic strength, characteristic basic strength, 15 tensile strength parallel the grade, and so on. So you have all the quantities you need there. So basically S1, S2, and S3 are a kind of strength, are associated with the strength profile, with the number of properties that then we will use in design. Why do we have so many properties? We will come back to this aspect here, but why do we have so many properties? Like here, I just remind you that for steel design, I don't know, I probably haven't done yet the steel design course. Okay, let's say for the concrete design, you don't have all this quantities here for design. How many properties do you need for the design of a reinforced concrete structure?
Can you repeat the question?
How many mechanical properties do you need when you design a reinforced concrete structure? So, which property do you need from the material to be able to do the design?
The strength?
Which strength?
Design strength.
Yeah, but the design strength is what kind of strength we are talking about? On which specimens? Okay, compression first. Compression, strength, on cylinder or cube, after we have the relationship. So compression strength, what else? Do we need tension strength?
No.
No, because if you remember there is an empirical relationship with, if you know the compression strength, you can calculate the tensile strength. So you don't need to do a test. Modes of elasticity. But do we really need the modes of elasticity? Also there, if you remember, there is a relationship between the compression strength and the modes of elasticity. But let's say that you need the compression strength for sure, and okay, you can have the modes of elasticity. Is there any other property that you need to, for example, to do the shear design? Do you need a shear strength for reinforced concrete? Shear strength. Do you need a shear strength for reinforced concrete? No. Compression strength and modes of elasticity. That's it. Then you design everything. And then, of course, if you design a reinforced concrete, what else do you need? The reinforcement
of the steel.
Yes. Which value? What do you need for the steel?
The characteristic, for example, the characteristic value of a snap.
The yield strength. Yes, it's called yield strength. So the yield stress of the bar. Do you need that? You need the actual tensile strength, the peak? No. Yield strength. And if you want the mode of elasticity. That's it. So basically, two properties to design all the reinforced concrete structure, two plus two other possible the modes of elasticity, but they are not so important. So here to design a timber structure, see we have 1, 2, 3, 4, 5, 6 strengths properties, going from bending to tension parallel perpendicular, compression parallel perpendicular, and shear. So 6 mechanical properties. Then we need 1, 2, 3, 4 shear modules, modes of elasticity. So we have modes of elasticity, mean modes of elasticity parallel to the grade. mean modulo of characteristic modulo of elasticity parallel to the grain, then modulo of elasticity perpendicular to the grain, and shear module, 4 properties. And then density, characteristic, and mean density. Why so many properties? Why do we need so many strengths, for example? Instead for conc we need only one value, for steel only one. What is the most important difference between the two materials? Yes, but not so much this. We could have also homogeneous material, but if the homogeneous material is anisotropic, then it comes to this problem here. So to have all the different directions and so on.
Because for timber, the property was to be homogeneous.
Yes, this is dishomogeneous. But what I want to say before, the reason why we have 6 mechanical properties is not the dishomogeneity, it's the anisotropy. Because all these properties here refer to timber, some timber, not to contrast. And still we have many properties. Why? Because it's anisotropic. Okay, it's clear? So for this reason, you'll see when it comes to do the limit state design, we will have different strength. If I do compression, tension, bending, I have to use different strength properties because the material has different strength properties. So, strength classes of some timber. There is a regulation, this is in English, EN 338 of 2016. So in general, this regulation, this is a European regulation, this provides for a number of strength classes, each designated by a number indicating the value of edgewise bending or tension strength Newton per square millimeter. So, you see, for softwood, so we have different tables talking about softwood, conifere, and hardwood, laying in the 95% of the wood that we are using now in Italy, I would say, is softwood, in Europe is softwood, 95% is softwood, so conifere. 5% is latifolia, hardwood. So the vast majority is softwood. So a strength class of softwood is designated by C, which is coniferous. For example, 18. What does it mean C18? It means this is a coniferous with a bending strength of 18 Newton per square millimeter. So the C classes are the classes that have been tested in bending. So if one piece of wood has been tested in bending, it's been classified in bending, then you use the notation C. If the piece of wood has been tested in tension, like you have a plank, the plank you instead of tested the plank in bending, you can test in tension, then the strength class is indicated with T. For example, T11 means that this piece of wood has been classified in tension and it has a characteristic tensile strength in this case. So this will be Fm, this will be Ft0. So F is strength, T is tension, and 0 is parallel to the grain of, should be this way, sorry, not F, should be greater. So it should be greater than 11 Newton per square millimeter. So a strength class, it's a class of material having a strength greater than or equal to the limit. Okay? So class T and class C. This is for T and C for, we said, softwood. Instead for hardwood, you test only in bending and you use the letter D. So this D40, for example. This is a class for a hardwood, so for example a beech, chestnut, so hardwood, with the main of the latifolia, with a bending strength, characteristic strength class greater than 40 Newton per square millimeter. Okay? Do you have some doubts?
Yes. C means conifers or
C
compression?
means conifers.
Conifers. And D?
T means conifer tested in tension.
Okay.
If you want, C means conifer tested in bending.
Okay.
T means conifer tested in tension. And D means deciduous, latifolia, tested always in bending. So this is the system of the strength classes according to this European regulation, as you can see here. So class, the symbols, so F, just a reminder, F strength, E module of elasticity, G module of shear, rho density. So M bending, K characteristic, and then T tension, 0 parallel to the grain, 90 perpendicular to the grain, C compression, B shear, longitudinal shear. You see, module of elasticity, for the module of elasticity, we have mean module of elasticity parallel in bending. We have 50% of module of elasticity parallel in bending, mean module of elasticity perpendicular to the grain, B shear modules. And the characteristic, the density, 50% density, characteristic density, and mean density. So, the important thing here to point out is this, that first of all, you see in bold, there are the most commonly used classes, strength classes in Europe, so C16, C18, C24, C30. The first line you see C14, it means 14 characteristic bending strength. Another important thing is that when you do, when we classify wood by bending, we always do a test we call edgewise test. So basically edgewise means that if we have a rectangular cross section, we test the rectangular cross section in the right direction. So we test as if it was basically spanning in this direction here, with the depth given by the longer side. So this is edgewise bending. We don't test in the wrong direction. Even though in the wrong direction, we can use exactly the same value of bending strength. Okay? Second thing, we usually test in bending. So we test in bending, and we measure the bending strength, the module of elasticity, like we saw before, with the displacement. So when we do the bending test, we measure the bending strength and the module of elasticity. And then we measure the density. The other quantity always measures the density. The density is measured by basically weighing the timber beam and dividing by the volume. So we have three values. So we measure bending, as we saw, module of elasticity, and density. All the other values that you see in this table are calculated using some kind of empirical relationships, not by us, by who wrote this code, based on this value that I said before. Other remarks, you can see that the bending value is in between the compression and the tension, like we discussed before. So compression is the highest value, the bending, the tension, obviously parallel to the grain. Tension perpendicular to the grain, you see constant is equal to 0.4 to all of them. Some regulations, like the New Zealand standard, assume no tension strength at all, so 0. Our regulation considers 0.4. 0.4 is very little, very little. Just to give an example, the strength of concrete in tension, which is low, we know very well, is 3. Well, that's 1/10 of the compression, 3, 4. Here we're talking about 0.4, so much lower. This shear is the longitudinal shear that we were discussing before. Module of elasticity, you see module of elasticity is quite low compared to concrete. Concrete, if you remember the normal value of module of elasticity for concrete. In gigapascal. Gigapascal, what was that? More or less. In gigapascal. 30, more or less, between 2.5, 3.0, 4, 30. Exactly. So you were talking about 3 times less. And then you see we have a module of elasticity parallel, mean and 5th percentile. Why do we need the fifth percentile? We said before that to calculate the serviceability limit state, so the deflection, we are going to use the mean value. Why do you think, or when do you think we may be using the fifth percentile of modulus of elasticity? Fifth percentile is usually used for what kind of limit state? Ultimate limit state or serviceability limit state? The fifth percentile.
Service limit state.
No. Serviceability limit state use the mean value, we said. For the serviceability limit state, we are using the mean value of deflection. Okay? It's always the mean.
The mean?
The mean for when I calculate the deflection, I use the mean value, never the characteristic. Because there are different coefficients for the serviceability limit state, it's always the mean. Now the question is, when do you think we might have to use the fifth percentile of the module of elasticity? The fifth percentile is usually used for which limit state? General? For? The fifth percentile means the characteristic value.
Okay. No.
Yeah, the fifth fractal.
Okay.
Yeah. So the fifth percentile used for which value of when we do what kind of design? For limit state, what kind of limit state? We use the fifth percentile.
No, not ultimate.
For ultimate limit state, which kind of value of strength do we use?
The design.
The design, but the design is calculated based on which value of strength?
The characteristic
Okay,
value.
and perfect. And the characteristic value, what is literally the characteristic value of a strength is what? Is the fifth percentile. So the fifth percentile is usually used for ultimate limit state verification. So in which case do you think we might have to use the module of elasticity, not the mean value, but the fifth percentile module of the module of elasticity? Which ultimate limit state? Is the module of elasticity affecting any sort of or any kind of ultimate limit state? We've been discussing this before. We asked you, what do we need the module of elasticity for?
For not the ultimate service.
This was one possibility. But then some of you said that module of elasticity is also needed for something else, not only for the deflection. Can you remember who was the person who said this? Not you. Someone else, yes. Yeah, someone said before that module of elasticity is needed to calculate the buckling resistance. Who said this? Who was the guilty who said this? Some of you said this. You. No, you. You. Okay, so you said it. So it's your fault. This is what? Okay, it's your fault. We found a guilty person. So you said that the module of elasticity is needed for the buckling resistance. Is that true? No, before you said no.
Before
You said yes. So it's true. Now the question is true? È vero or no?
no.
Male. Because it's true. It was true actually. The module of elasticity is needed for calculating the buckling resistance of a member. If it's needed, since this is an ultimate limit state, which value of module of elasticity we will have to put into our Euler formula? You remember the Euler formula? E squared times pi divided by L squared. We will have to use inside, since this is needed for ultimate limit states, we have to use inside the characteristic value of the module of elasticity. So the characteristic value of the module of elasticity, this one, is needed when we are going to do the design for buckling. Because in this case, we won't find in the formula the strength, we will find the module of elasticity. And then we will have to use this value, the characteristic value. Then you see we have a module of elasticity perpendicular to the grain and the mean shear modulus. Mean shear modulus will be used to calculate the deflection. Okay, so let's try to conclude because it's late. Those are the strength classes. You see T strength classes. In this case, we have that our pieces of wood are classified. These are softwood pieces, so softwood classified in tension. So T, for example, 11 means that we have a piece of wood which has 11 megapascal of characteristic strength parallel to the ground. What is the bending strength? The bending strength is more, 17. And here we have all the profiles. When it is used, when may be useful to have a classification in tension rather than bending? Classification in tension is useful when we have to classify planks, tavole. Tavole, planks, then will be used into glue laminated timber member, so in legno lamellare incollato or in cross. Why? Because in a glue member, if this is your glue member made from different planks, when we know this cross-section in bending, we will have a distribution of stresses, the same convention like before, and as you can see, the planks will be subjected, this one, mostly, you see, this one. What is the stress distribution on this plank here? It results from bending, tension, or tension and bending coupled together. If I ask you, look, this is a stress distribution here. So, this is my cross section. This stress distribution here, where does it come from? Does it come from tension, from bending, or from tension coupled with bending? Perfect. Tension coupled with bending. If I had to ask you, is more tension or bending? Much more tension or just a little bit more than bending?
More tension.
Much more tension. This is almost only tension. Strictly speaking, it's tension coupled with bending, I agree with you. But if you look here, the bending is only this. It's mostly tension. So when we use in a cross lamp, it's clear? It's clear, it's mostly.
Sorry, these are planks.
These are planks. So this is the cross section. Sorry, I'm rushing. I don't want to stay too long. But this is the cross section of a cross lamp unit. So basically, what is the specimen? No, it's not the specimen. I'll give you another thing. This used to be a cross lamp beam. Then someone of you, not you, but another class, they dropped off and lost one piece. There are planks glued together. This is called glue lamp, legno lamellare incollato. So this is glue, so the cross section is the same. So these planks are mostly subjected to tension. So when it comes to basically do a glue laminated cross section, it's better to know the actual tensile strength of the plank rather than the bending strength, because in the end, the plank is mostly going to work in tension in the cross section rather than bending. It's clear? So for this reason, we use for the planks mostly these classes here, this tensile classes here, T10, T11, so on. Those are the classes for the deciduous trees, we said before, for hardwood. You see there is much higher strength here, you can get up to 8 huge value. And then you see the allocation of a population of wood to a certain strength class. A population, this is a population of wood specimens, may be assigned to a strength class if its characteristic value of strength, mean mode of elasticity, density, equal or exceed the value for that strength class given in table 1, 2, or 3. So what does it mean this? Let's go to C. You see here, for example, this is an assignment of visual grades and species, always taken from this regulation. For example, suppose that we have in Italy we have Douglas. So Douglas is a legno di Douglas. It's a kind of wood that can be found on the Apennine region, particularly in Tuscany. So this wood here see, the Douglas fir, if we classify Douglas fir according to S1, if you remember before, we have these three classes, S1, S2, S3. Suppose you have a wood, Douglas fir wood, and you classify, you do a visual grading, and you classify it S1. So S1, you see from this table, is directly associated to C30. So, if you go back to this table here, this one, so S1 class of Italian Douglas fir is automatically assigned to this strength class C30. So, suppose you get your Douglas fir, you check, you do all the visual grading, you find out that this can be assigned to S1. It can be assigned to S1. Automatically, this can be considered as C30, which doesn't mean that the bending strength is 30 megapascal. You have all this strength profile here. And then, of course, you have all other cases, like other cases, growth and so on, in this table here. What I was saying before is that in general, I mean, I'm going fast on this here because this is just an example. As I said before, this is not the main job of an engineer to do this kind of thing. But nevertheless, it's good to know, as I said before, because when you will be a check engineer, you might have to do some of this visual classification. Before I was telling you that in general, for the softwood or for the hardwood, what we do, we measure the bending and we measure the modular elasticity of wood. Now, once we know the bending and the modular elasticity of wood, we can find all the other quantities of the table, you see, tension parallel to the grain, tension perpendicular to the grain, so on, using this kind of empirical relationship. So there are some empirical relationships that was developed by wood scientists over the years. So once you know, for example, that the bending, you measure the characteristic bending capacity, then you can find out directly the tension parallel to the grain resistance, and so on. So there are this kind of relations given by the regulation. You see also this is interesting. If you measure the modular elasticity, like we said before, you have a beam, you know the beam, you measure the modular elasticity. This would be the mean modular elasticity parallel to the grain. How can you calculate the characteristic modular elasticity? So the fifth percentile that we need then to do the buckling verification is basically 2/3 of the modular elasticity parallel to the grain. How do you calculate the modular elasticity perpendicular to the grain? 1/30th. So modular elasticity perpendicular to the grain is only 1/30th of the modular elasticity parallel to the grain. It's very low. Just remind you that modular elasticity of wood, we said before, is 1/3 than the modular elasticity of concrete, parallel to the grain. Perpendicular to the grain becomes 1/100th, because it's 1/3 of 1/30th, so 1/90th, so 1/100th. So very, very little. Mean shear modulus of this is very low, E divided by 16. Does some of you remember the elastic relationship that you studied in solid mechanics between G and E? Remember solid mechanics with Professor Longo? G equal to E divided by what? Divided by 2 times 1 plus ni, or nu. Ni, which value? More or less. Could be between -1, which doesn't make physical sense, till 0.5. So if we do G equal E divided by 2 times 1 plus 0.5 will be 2 times 1.5 will be 3. So for an elastic and homogeneous and isotropic material, the modular elasticity is 1/3. Sorry, the shear modulus is 1/3 of the modular elasticity. Let's see here, 1/16. So for an anisotropic material like here, G is not 1/3 of E, it's 1/16 of E. So it's much lower. It's basically 16 divided by 3 is 5 times lower. So this should make you think about one of the hypotheses you did in mechanics of material, in scienza di costruzione, solid mechanics. When you calculate the deflection, just remind you that you were told, is it important to consider the shear component of the deflection? You calculate at the beginning, then you find out that it was negligible. Will be the same here for timber. For timber, it's a little bit different. In that case, it was 1/3 of E. Here is 5 times lower. So perhaps for timber, we should think that maybe this shear component of the deflection may not be negligible, like for all the other materials, like what you have done with the colleague, Professor Longo, from mechanics for mechanics of structure. In fact, you will see that in this case, we will have to consider for timber because G is much lower compared to the case of the normal isotropic material. Okay, so I think it's a good point here to start, unless you're really looking forward to see what this slide says. You don't feel so much curious now, perhaps it's the time to study. So I think if you don't have, do you have any questions to just about what we've done before? If you really want to know. Okay, so if there are no other questions, then I think we can stop for today. So this week, it's only me, so next lecture will be the day after tomorrow, Wednesday. They're always here. Right? Wednesday morning. Or Wednesday after, I don't remember. Anyway, what is in the table? That should be Wednesday after. Okay, the idea is that if you can, it would be very nice for you, if you can, to read in advance what I'm going to talk. I know that nobody does, but I can tell you that if you can read in advance, then the lecture is much more fruitful for you because you listen from me something that you have already read a little bit. Maybe perhaps you haven't understood everything, but it would be very nice and you would have memorized what we are saying here. So if possible, we will have to read. Now next time we'll just continue this lecture. So it will be. Okay, grazie.